Okay, so let's finish what we started last class. So last class we talked about esters, and we saw that we can make esters from carboxylic acids under acid catalyzed conditions, and that this reaction is entirely an equilibrium reaction. So we will need to remember that. In a little bit we're going to see, actually in a very little bit, we're going to see the hydrolysis of esters. So we made the ester from the carboxylic acid, and the acid catalyst was used to protonate the carbonyl oxygen, which activated the carbonyl group so it could be attacked by a weak nucleophile, in this case the alcohol. And we went through the mechanism on the board, and this is the mechanism. So the activation of the carbonyl compound by the acid, it can then get attacked by the alcohol, form our tetrahedral intermediate. We get a series of protons jumping on and off until the proton's in the right place. And once it's there, it can lose water and give us what becomes just our protonated ester. Loses the proton, and we get our ester. This thing is entirely an equilibrium reaction. We can make esters from other things. We discussed again, the activity chart. We're going to see it in a little bit when we talk about amides. Remember, we have these carboxylic acid derivatives, and we have very reactive ones, like acid chlorides, and we have very stable ones. Esters are pretty stable carboxylic acid derivatives. They're fairly stable, and in fact, a very common solvent is ethyl acetate. Oops. This is ethyl acetate, or ethanoate. Okay, so we can make it from more reactive carboxylic acid derivatives by reacting a carboxylic acid chloride with an alcohol. We do it in the presence of something that's going to sop up the acid that's formed, because when we form this reaction, HCl is the byproduct, and obviously if there was any water around, that would then be hydrolyzable, because these things are sensitive to acid under conditions in which water is around. So we use something that sops up the acid as it's formed. You will learn in later years that this thing also acts as a bit of a catalyst. It can also, it is a nucleophile, will attack the carbonyl group and form a compound that is quite labile and promotes the reaction. So acid anhydrides are also more reactive than esters, and we can make esters by taking an acid anhydride, in this case acetic anhydride, reacting it with oh, that's a mistake. That shouldn't be benzoyl chloride. That should be benzyl chloride, okay? I just noticed that now. Benzyl chloride. There's the benzyl group, the benzoyl group. That's the benzoyl group, okay? Just a couple of mistakes. So we can take acetic anhydride, react it with benzyl alcohol, and we'll get benzyl acetate. And we still get an acid product. In this case, it's a weak acid, so it's not as bad as making it from the acid chloride, because this is a weak acid. It's less able to catalyze the hydrolysis, although we still have to be careful. So we can do the reverse reaction because that thing was in total equilibrium. If we take the ester under acidic conditions with lots of water around, we're going to hydrolyze it. We're going to break it up into the carboxylic acid and the alcohol. We've added water to this molecule, so we've added H to here and OH to to make our carboxylic acid and our alcohol. And the mechanism, you guys should be able to figure out by now, but the mechanism, what's the first step in this mechanism? Can anybody tell me? We have our ester, and we're reacting it with water. What's the first step in the reaction? In this case, I'm going to do this. I'll use a specific one. So what's the first step in our reaction? Anyone? Okay. We can attack the carbonyl, but this is a weak nucleophile. What do we do when we have weak nucleophiles? What do we do to the carbonyl? We activate it. Whenever we see a proton around, remember, we want to do something with it. And in this case, we activate our carbonyl. Once we activate our carbonyl, it's susceptible to attack by even a weak nucleophile, such as water. And I put a couple of steps here just to indicate that this is more than one step, but our proton is just going to pop off and then it's going to pop on. Might pop on up there, might pop back on there. Either way, that just leads to the reverse reaction and leads back. But when it lands on the alkoxyl functionality, we now this can leave as an alcohol, and we can just push it off. And there's our alcohol product and our protonated acid. And finally, that just loses its proton at the end. And here I'll put minus H plus. So we get our carboxylic acid and our alcohol. Notice that our H plus adds here, it jumps about, but at the end it comes off. This is an acid catalyzed reaction. We don't need a full equivalent of acid. Okay, that's important. And here's the mechanism on the slide, so that we just did. We can also do this reaction under basic conditions, in which case we have what we call a saponification reaction, and that comes about. Does anybody know how you make soap? When I was a kid, actually, my grandparents still made their own soap, and you just get a bunch of animal fat, and you'd throw ashes in, and you'd boil it to pieces, and then you would end up making soap. The ashes were actually to get base in there. There's base in the ashes, and the base, this should be a negative, by the way, the base is what promotes this reaction occurring. So how does this happen? In this case, I'll use the same compound we just used. I'll put the electrons here initially and then stop, but we have our negatively charged hydroxide. We don't need to activate the carbonyl compound in this case. And as soon as we're under basic conditions, we don't want to see any H plus in any of our mechanisms really, because everything's going to be a negative species. If you see an H plus, you should have 2 minuses somewhere else, so you want to be careful. So we can attack our carbonyl compound, form our tetrahedral intermediate, I'll put the electrons there. Okay, we can then, this is our tetrahedral intermediate. We can reform the carbon-oxygen double bond, and if we kick off the hydroxide, we just come this way. But instead, we can kick off this thing. And we form our carboxylic acid. And this is the important part of this. This is what drives this particular reaction, okay? This one can't really go back. I didn't draw an equilibrium area here. It doesn't go back. Why does this one not go back? What happens instead? When we have a weak acid, but it's meeting a very strong base. What happens when a weak acid meets a strong base? What kind of reaction do we have? Do we have a nucleophilic addition to a carbonyl group when a weak acid meets a strong base? Or do we have an acid-base reaction? Okay, so we would have our acid-base reaction. So this reaction really does not go backwards. I'll throw it up here in just a second. So we end up with our carboxylate Dustin, you'll have to bleep out that expletive. So this last step drives this reaction to completion because we have a strong acid, or I'm sorry, a strong base reacting with it's a weak acid, but because we have such a strong base, it drives the reaction to completion. The difference between this now, this reaction is not base catalyzed. We need one full equivalent of base for this reaction. It's base promoted and it needs a full equivalent of base because the base gets used up in that last step. The last step drives the reaction. So that's an important concept to understand in these reactions, what's driving the reaction. With this reaction, the acid catalyzed esterification, what drives this reaction is the fact that we put lots of water so that we shift the equilibrium to this side. And in fact, we can make esters from this same reaction mechanism by doing it under conditions of which we have little or no water around, and the only water that's produced is during the reaction. And then, even then, we may be able to have methods of sopping up that water. So this is the mechanism we just went through. Sometimes we can make esters from an acid and an alcohol that are attached. Okay, so I'll go through this mechanistically on the board. But we have up top here a delta hydroxy acid because we have a hydroxy group on the alpha, beta, gamma, delta carbon. So what we can do then, the first step of this reaction is to promote, to activate the carbonyl. So I'm going to draw this just a little differently just to start out. There's our protonated acid. And this is the alpha, beta, gamma, delta carbon. We have a hydroxyl group on the delta carbon. And I've just drawn this to show how easily the hydroxyl group can gain access to the carbonyl carbon.
Can you run us through why the second carbon, not the carbon that's attached to the oxygen, is the alpha carbon?
Because it's all relative to this. This is the carbonyl carbon. And when we talk about an alpha carbon, just like whenever we talk about an alpha carbon, we're talking about it relative to some functional group. If we had an alkyl bromide, the carbon with the bromide would not be the alpha carbon, it would be the one next to it. That's all. So that's all you have to remember. Nomenclature-wise, we typically talk about carbonyl compounds a lot. We'll use the alpha, beta, gamma, delta designation. So we can see that I've just drawn this, and I'll just draw it the once. I've drawn kind of a pseudo chair structure. This is to show how easily we can reach a conformation in which the oxygen has access to the carbonyl carbon, and we just get this, and it's protonated, by the way. We just get this intramolecular oops. Now, where's my R group? Can anybody tell me where my R group is? So this carbon is the carbon right there. Then we have alpha, beta, gamma, delta. There's our R group. The other way to think about it was the R group was on the same carbon that had that oxygen. Okay. So we've now formed this intramolecular compound, and some base comes along. Oops. Sorry. The next thing that happens then, what's wrong? Oh. I had an OH here, and I have another OH here, right? Okay. So we have two OHs coming off of here, and then we get a proton shift that occurs. Let's get rid of this junk over here. Let's draw a couple arrows to there because we realize that a proton comes off and a proton comes on.
Is your R group not coming off of the delta carbon?
Sorry. What's that?
Like is that, I think it's an 8, it looks like an 8. Is it supposed to be?
This?
Delta?
That's delta.
No, the second row.
Here?
Yeah.
Yeah. So alpha, beta, gamma, delta.
And what's the other structure?
Oh, sorry. Sorry. That's a positive charge.
Thank you.
Okay. Now our positive charge has moved over to here because a proton popped off, floated around, something carried it, and deposited it over here. Once it's over there, we can just knock it off as a water molecule. In the final step, we just lose the that proton in the final step to form our lactone. And that thing's called a delta lactone. And it's called the delta lactone because the oxygen, it came from a delta hydroxy acid. Okay, and lactones can be hydrolyzed under aqueous conditions. We can make these things go backwards by swamping them with water, just like we can for any ester. Notice the mistake here, we can do it under acid catalyzed conditions or base catalyzed conditions. They talked about it being hydrolyzed by aqueous base, and then they show this thing happening under acidic conditions, and their product is under basic conditions. So there's a mistake in the slides that I pointed out. This should be, there should be base here. And we're not going to worry too much. Now the last one I want to talk about is amides. And we're going to talk about amides a little bit more extensively, so this is not a bad place to stop. We'll look at the simple ways that we can form amides. We can form amides from any of the carboxylic acid derivatives that are more reactive than amides. And as it turns out, all of these are more reactive than amides. So we can react any one of those with an amine, in this case dimethylamine, and get an amide. I'm sorry, I made a mistake there. There should be an R on each of those, or not, whichever we prefer. So mechanistically, how does this happen? It happens the same. It doesn't matter. We'll do the first one with this acid chloride. So we have pH. And I have a dialkyl amine. We don't really need to activate this carbonyl because it's quite reactive. We can attack the carbonyl compound, and when we do, we'll get this Vitter ionic species. And this can go backwards or it can go forwards. When it goes forwards, we get this thing. Now this is important. We have Cl minus. So we have to remove our proton. What's going to remove our proton here? Chloride is not a very strong base. What about amines? Are amines strong bases? Amines are strong bases. So what happens here is, in this case, we have some other amide. Well, not some other amide. And this gives us pH.
Should there be arrows on that chlorine second structure?
Yes. So we end up with this ammonium chloride salt for our final product. So what we have to realize is that we need two equivalents of amine, or we need something else to sop up the HCl as it's formed. We could use pyridine as well to sop up the HCl. And that's actually what they show in this first reaction, a little less obvious, but we need two equivalents of amine. We need our initial amine, we get down to here, and we need another amine that pulls off that proton because the Cl is not going to pull it off. The HCl is formed, so we end up with our HCl salt in the form of an ammonium chloride. The same thing really occurs with anhydrides as well. We also need 2 equivalents of amine, and in which case our final products are the amide as well as the carboxylate, the ammonium carboxylate at the end. Okay? Because we get this acid product, and amines are good bases, we have to use twice as much amine because one of our amines ends up as a salt with the conjugate base of the carboxylic acid. I just wanted, I meant to hide those. We can make amines from esters. In this case, we don't necessarily need, an extra equivalent of the amine because our product is an alcohol and an amide, and this is a very, very poor acid. It's not a strong enough acid to protonate the amine, so we don't have to worry so much. We sometimes may want to put in a little bit of an acid catalyst to make this reaction go a little faster because we need to promote the reactivity of the carbonyl carbon, and we can do that by activating it with a little bit of acid to get the reaction going. Now, in this case, you couldn't do it. The other thing that's convenient is if you have a high boiling ester and a high boiling amine, which you don't have in either one of these cases, and then your alcohol product is low boiling, you can make this reaction go by adding enough heat so that you can boil off the methanol and everything else remains in the pot, and it's a convenient way of driving this reaction to completion. One of the things I wanted to show you too, wanted to remind you actually, is, and it's not necessarily here, don't forget to look in the bottoms of your slides. So there's quite often links that provide mechanisms other than the ones in your slides, because the ones in the slides are a little bit messy. Over the summer, I hope to build up my own set of slides because I'm not really particularly enamored with these slides. I think we're going to stop there. Yep. Yeah, we're going to stop there because